Group 16, and Ethan Madden, Claiborne Struck, Solinger, James Wheaton, Paul Davis. We decided to make a perpetual motion machine that was invented by French architect Villard de Honnecourt in about 1235 AD. And we chose this because we wanted to keep things simple, and as you can see, it's just pretty much a wheel with a few hammerheads on it to help it continue spinning. In theory, it's supposed to spin forever, but due to friction and all these other types of things, it'll only spin like once maybe. But still, it has some pretty good motion. We could even add a motor if we wanted to, but we decided to keep it simpler, so just put a crank on it so you can just crank it. Only the most complex thing on here was pretty much just the hammerheads. And that's pretty much it.
Well, it's a little more complex than that. A lot of effort went into the actual design process of how to design the hammers, because we had to make it so that when the hammers went forward, they would contact with the wheel, but also so that when they fell backwards on the opposing end, they wouldn't hit each other. So this was actually this little plane right here was designed so it would contact the wheel at the right point so that the hammers wouldn't fall too back. And the shaft itself of the hammer is done with variable section sweeps and boundary blends, mostly to smooth this area right here out, and then I'll just talk about this particular hammerhead. It's done with boundary blends and a variable section sweep, along with the P right here. The P is actually in there, one for looks and two to reduce volume. It was very important that we kept all the hammers approximately the same volume for symmetry purposes. So we had to take a lot of that into consideration as we were designing the hammers. Second would be we did a basketball. And this one was actually a little more difficult with the laces, because these laces were very hard to actually model correctly to how a basketball looks. And it's actually a series of projections and sketches where all the laces were sketched, and then in order to make this sort of point right here, this contact point, a line had to be projected on the surface, and then these had to be resketched, and then a variable section sweep was used to actually cut out the laces. And then the Big Ten projection is just we projected a sketch plane, or we projected a plane from the ball and then just extruded the Big Ten to that plane. And it actually didn't show up very well on the physical model. I think some of it got cut off as they were cutting the individual hammers out. And then Clay is going to talk about the football one.
In our original design, we actually had only Purdue hammers going around, and then we got to thinking that we wanted to add a little bit of just another look to it. And since we went with the Purdue theme, that's where we got the idea to do the football and the basketball. This guy. And so what ended up being most difficult about this is since we decided to do multiple designs for the hammers, we then had to, instead of making a part, we had to make a base hammer that then could be used by all of us making the different hammer tops. So I made the football, and we tried to make it as real as possible. And the most difficult part of this was actually making just the shape of the football. I did it first with the revolve, but then we found out, well, you don't want to do a point with the revolve. So that had to be modified using tangency at the ends of these, basically making the curve come to a tangency point going vertical, so that when it was revolved, it actually made a complete surface. And then the lace that is on the football was made, like he said, similar to the basketball, with the projected curves and then cutting out. And the laces on the top took a long time to figure out how to pattern both ways. For some reason, using CATIA, it was easy to figure out how to pattern, because I think if I remember at the original model, or the original surface, you could then pattern again. Because I made one of these and then wanted to pattern it along a curve, and I was able to do that one way and could not get it to go the other way. And eventually, though, we figured out that you can just pattern a pattern. So that worked out nicely, and it came out. And then getting the football onto the hammer, basically we had to copy the surface and the sketches into the base hammer that we had made so that we could all use the hammer. And then by projecting curves and then sweeping the curves, we were able to get a kind of a seat for the football to fit in so that we could constrain it and it kind of form fit to the hammer, so it didn't have just like it wasn't just sitting on top of like a plane. So that is that. And now James is going to talk about the complete assembly.
Okay, so the assembly is pretty easy. You just got like pins around here. There's a pin here, and right now you can drag it like this, just like you would in real life. Some of the problems that we ran into was that you can't pattern the connections. So, for instance, I was patterning this pin, and it worked on all the other ones, but on the original one, it just stayed static. So I had to do it individually. The other more difficult part was constraining the motion of each hammer. If you just put a pin here, it would just rotate all the way around, and I did the animation for that and it looked pretty crazy. So what we ended up doing was creating this spline here, which is just like a semicircle, and then it's kind of like a slot connection, so then you can only move it like that. So let me show the video. On getting the animation was pretty tricky. Yeah, so even just putting in the right amount of torque was hard, and since we use gravity as a part of the main motion, it was really computationally intensive. It took all day just to make this video, and you can see it doesn't actually perpetually spin.
Yeah,
in the
just a
animation.
20-second video was probably 12 hours worth of computations.
So yeah, it was hard to guess the torque. Like, this is 500 inch squared pound mass per second squared.